we introduced the eigenvalue problem, which is this little matrix equation down here. A is a square matrix, K is a column vector, lambda is a scalar. And at least one motivation for doing that was it can be used to solve a system of linear homogeneous equations with constant coefficients. This example was 2 by 2. And so we need to find two things here. We need to find all the lambdas that make this true, and then the corresponding k's that make this true. So we need to find lambda and k. And we did this little bit of algebra in the previous video, which said we need this to be true. This determinant of this little matrix here, A minus lambda I, has to be 0. And that was because we don't want the trivial solutions where k is just 0. So this gives us a way to find the lambdas anyway. We still have to find the k's. And by the way, what does this matrix mean? A minus lambda I? It means you subtract lambda from every diagonal element of A. So let's do an example. Here's our A. A minus lambda I means subtract lambda from the diagonals. The rest of it stays the same. So inside here is A minus lambda I, and we want the determinant of that. You can do a determinant, right? The product of the main diagonals minus the product of the off diagonals. That's how you do it for a 2 by 2. You get this little equation. It's quadratic in lambda. I can multiply it out, do some simplification, factor it, and I get this equation, which tells me the lambdas that solve this are lambda equals 0 and lambda equals 3. There are my eigenvalues. You're going to get as many as n. This is 2 by 2. You're going to get 2 eigenvalues. We'll talk about, they could be repeated. We'll talk more about that later. But if it were 3 by 3, you're going to get 3 eigenvalues, etc. You're going to have to do some probably solving quadratic equations, do some factoring or use a quadratic formula, etc. What about the special case where your A matrix is triangular? Well, A minus lambda I is going to look like this, right? You're subtracting lambda from every diagonal element. I can find this determinant by expanding by this first column, and everything's 0 except this term here, which says, okay, pull that out, and then take the determinant, the minor determinant that's left, which is going to be all this stuff down here. It's going to look like this, which is going to look like that, just with a different first column. But now you expand it by this first column. So you pull that out, and this is the minor determinant that's left. You keep doing that, and you just get this, which is all those diagonal terms. If it were, let's see, this is upper triangular. If it were lower triangular, you would just expand by rows instead of columns. So we have an easy method if your A is triangular. Easy method of finding the lambdas, the eigenvalues, instead of having to do all things like factoring, etc. You just look at the main diagonals. Like in this case, I don't have to find a determinant. This is lower diagonal, so the eigenvalues are just 3, 2, and 1. Those are called distinct eigenvalues. Each one none of them are repeating. There's 3 eigenvalues with 3 different values. What if it were like this? 3, 2, 2. You still say it has 3 eigenvalues, but one of them is repeated. You have 2. So that's why I say you're always going to get whatever the size of A is, n by n, you're going to get n eigenvalues, but some could be repeated. Okay, we'll get into how to, so now we know how to find the eigenvalues. Next video, we'll talk about how to find the eigenvectors.